So, my job here is to tell you about simple machine learning. Quick caveat, I'm not an expert, and that's why this should hopefully be a bit more interesting. So, who am I? I'm a senior software engineer at DataSift. I look after the web application for controlling everything, the public API, and a bunch of internal services. Prior to that, I was at Time Out magazine and working on CRM systems for secured loans companies before that industry fell through. I'm also the founder and co-organizer of PHP Berkshire. Another co-organizer there. Yeah, if you want to head out to Reading, then we're more than happy to welcome you all the way, all those 20 long minutes away from Paddington. I also act. For the record, it's not group therapy, it's not individual therapy, it's me being a dog. I do have the hair for it. So yes. So, the challenge. I call this talk Simple Machine Learning because machine learning itself, at its basic, is actually quite straightforward. There's a bit of maths in there when you get to some of the classification stuff. There's a bit of probability theory and stuff that we can just say, well, here's an equation, let's chuck stuff in and forget about it. But in essence, it's a very straightforward process. But in order to kind of apply this challenge, I've got to have a case study. And the one that kind of kicked me off in thinking about this now and in PHP and so on was a blog post by Larry Garfield in August when he looked at the number of new speakers at PHP conferences throughout, since 2011, I believe. He basically grabbed a bunch of data, which I'll show in a sec. The joined-in API he used, he grabbed all the events, all the talks, and he used that, given that it's vastly PHP biased, because it's written in PHP, it's promoted by people from PHP, and we all love our own. He did an analysis of first-time PHP speakers across all these conferences, and he came up with a number of about 51% new speakers. I've run that code again in the past few hours, and that's actually running now about 49%. So still doing pretty well, but one of the things that joined in is it's not just PHP focused. It's built in PHP, as I said, it's promoted at PHP events, but there's some rather large conferences in there. There's that don't say anything about PHP. There's JavaScript stuff in there, C++, there are away days for people like Invika, and so on. So a lot of that data is actually not quite focused on PHP in the way that core assumption is made. So there's a tagging system in joined in. You can say this talk is about, or this event is about PHP, this one's about JavaScript and so on. But we have a bit of a problem. We have only, out of 1,084 events, we only have 409 of those are tagged. The majority are untagged. So we can't just go and run this analysis by looking at the tags and seeing everything that's tagged with PHP and improving our results in that way. So we've got to look at how do we make up for the 675 untagged. And then going forward, unless we start enforcing tags on joined in, how do new events start getting tags? And how do we kind of keep classifying things as we go through? So there are a few solutions. Number one, the most boring one, is to go through 1,100 talks by hand and tag them individually. If you estimate 1 a minute, you can do it a bit faster, but if you estimate 1 a minute, that's 11 hours of work. You might find typos or have typos in your tags. You might not apply your criteria consistently, and as such, you're prone to a bit of error there. Then, once you finish classifying everything, that's great, but 20 new conferences or 15 new user groups have sprung up in the time it's taken you to tag those events. So that solution isn't exactly one that goes forward, and it's not necessarily one that really scales. No one really wants to be there going, right, so I've got to spend an hour tonight tagging all the joined-in events. It's not fun, it's not cool. It's not an appropriate use of our time, perhaps. We have Mechanical Turk. Hands up if you've heard of Mechanical Turk. That's about half of you. So Mechanical Turk is a system, kind of a system that's put forward by Amazon, where you put in kind of micro jobs. You say, here's some background, here's the output that I want from that. It distributes it to real humans, and then they do your work for you in little bits. So it's quite scalable. It's done by humans, and it's applying that kind of the human eye that we'd like, but again, you have to pay for such a service. It can get expensive if you need to get a lot of people contributing, and you need to get a lot of stuff checked as you go through. It is fun, it is cool, but again, expensive, and you're relying on others and their interpretation. It could just land in the lap of someone who has no idea what PHP is and couldn't tell you that a symphony talk, for example, is about PHP at its core. So our third solution, and the one that you're here for, is machine learning. Yay. It's fast. Well, it's fast when you apply it, as we'll see in a bit. It's consistent, so once you've got your model, it can be applied time and time again, and you'll get the same results. Automated, and it is fun and cool. There we go. That's our selection criteria for our solution. So, before we pick up on machine learning and what that is and how that works, let's have a think about how we, as humans, learn, because ultimately what we're trying to do is come up with a model that models the way we as humans look at the input data and how we can understand and interpret that and apply our learnings as such. So, how do we, as humans, learn? Pattern recognition is a huge part of what goes on up here, and not just this one ball of yours. We spot patterns. We see cause and effect. We associate, well, this happened, then this happened, so if we see that enough times, we make that link that cause caused that effect. And correlation in our brain, anyway, is causation. And the mere fact that we know that that's not the case, and that's being propagated, correlation is not causation, is quite, it's the phrase, that's because we have to subvert that innate way that we think and the way that we make those connections. For example, pigeons, you can make them superstitious. If you feed them every time they turn 360, when they're hungry, they'll turn 360 just to get the food, if you do that enough times. And that, at the basis, is the way that we learn. We also look at past experience. We build a mental model of how we experience the world and the people and the places and the things that we encounter. And we create stereotypes. And again, we were hearing about biases in the keynote. And some of that is learned from our experience, and we might have some bias from our own experience and some stereotypes from our own experience. But that's the way that we deal with the world in a general sense, in our kind of type 1 immediate sense. And one of the examples of this pattern recognition is something called Baader-Meinhof, not the terrorist gang, but another way of looking at things. It's basically where you learn a new word, or you encounter a new brand, or you shop at a new shop. You've never heard of it before. It's never been important to you before. Suddenly, it's become important to you, and you're very aware of it, and you step out of the shop with your bag that's got the name of the shop on it, and you go, I'm really cool. This is the first time I've seen this new shop. And you look around, everyone's got bags with the name of the shop on. You learn a new word, and suddenly you see that word everywhere, and you wonder, why haven't I encountered that before? And that's because we attach importance to the new things that we've encountered. The other way, or another way that we learn is through shared experience and teaching. So being instructed about things, being told that this is the way that the world works, being told this causes that, and gaining that information from an authoritative source. It gives you that gateway into the ideas. And because it comes from a teacher, you know that, well, you hope, assuming you're in a good educational system, that there's authority there and that what they're telling you is correct. And from all that stuff you've learned and picked up on, you can apply that model that you've been taught to the rest of the world. Because you've got the authority, you then have accuracy, we hope. And also because you're doing it in conjunction with a teacher, you have those opportunities to fail and to be corrected. And that kind of feedback loop helps us to learn and to refine our model as we go through. So, machine learning. It's not as scary as it sounds. Some of you might not think it's scary, but it's straightforward. It's a chunk of break down a problem, figure out how to build a model of it and how to apply that model to get the output that you're after. The things we're going to talk about aren't going to be as advanced as neural nets, mainly because I don't know that stuff. I'm going to pick through one example of how we build classifiers and how we apply stuff. But one of the things that I realized when I started tackling this is, actually, I've been doing this on and off in various guises for years. I've been looking at how often things pop up. I look at the correlation between some items, and then I can make a prediction off the back of it. So I was doing this. It's a big buzzword now, but I was doing this without calling it as such 12 years ago, trying to do image recognition at university in that project that I don't understand anymore. But that kind of, the fact that it's been around, well, pretty much as an idea since the 60s and 70s, it's only just becoming scalable and practical as an approach that we can pick up. There are a couple of different types of machine learning. There's unsupervised learning and supervised learning. So unsupervised is where you just say, here's all the input, here are all your documents, all your events from joined in. Go off and figure out something. Just leave it to its own devices. And the way that kind of works is you might think, take all the words that come in, look at the similar words that come up, and group all the events under similar words, then pass it off to a human to label what those clusters are, find similarities between documents and lump them together, and then present those, or find inherent connections between those clusters and present that as kind of a network diagram of all the events there. It does help uncover hidden structure. One of the cool ones that has been described in the past few years and is now being done at scale is called word-to-vec. And effectively what that ends up doing is you give it a load of words, a load of English words, if you like, loads of text. It starts figuring out the relationship between individual words. And it's above me and over my head, but what you get at the end of it is this kind of spatial model of words in our language. And it inherently, without actually knowing that male and female exist, it can start to cluster the words around there and start to, I say, gender words, so it can connect female to queen and male to king and royal to king and queen. And then you can do some fun stuff, like give me all the words that are royal minus male, and it would give you queen off the back of that. Like I said, over my head, so that's my simplistic understanding of it, but that's a good example when you come across it of unsupervised learning. Supervised learning is where you actually do that teaching. You say, here are all the documents, but here's a set of documents I've done for you. Here's a set that I've actually pre-labeled. In our joined-in example, we've already got some events that are tagged, as I said before. So we can think of that as being our source of authority and good set of labeling. We build our model from those known accurate knowns, to borrow a phrase from Donald Rumsfeld. And we take that model that we build from it, we refer to that, and we take all of our assumptions from that, and we apply that to new documents that come in, new things that we come in, and take that stereotype that we built and apply it to the new stuff. And it's important to know that it's the fact that we've attached metadata in those labels, in those tags, to our documents that's the supervised part. You can have interactive and non-interactive supervised learning, and the important thing is that you've told it about some of the relationships already and the kind of relationships you want to bring out. There are a few types of output that we can look at from our machine learning. So we have regression, which is basically line of best fit. So you plug a load of data in, you say, here are my independent variables, or are they dependent, and figure out exactly what the relationship is without understanding that up front. So if you know that the temperature of a room goes up when a lot of people are in, and you have a number of people, and you have the data that you could correlate the number of people in the room versus the ambient temperature in the room, then you could build a model via regression, linear regression, to actually predict the temperature of the room given the number of people come in, without actually doing that working out for you. It's a very simple example, but if you imagine extending that to a lot of different variables where you'd be there all day by hand, plugging all this stuff in and looking for those different pieces, machine learning that does regression is one way of figuring all that stuff out. And it's used for those continuous values I talked about, temperature, but anything on a spectrum, basically, where it's not discrete, this is a this is a that, and so on. It's, here's a predicted output value. Then there's classification, which is what we were looking at, tagging. So you say, these sets of documents belong to this class, this set of documents belong to this class, and as a result, when I give a new document, which class does it belong to? You can think of it as which bit in the library do I put this book into? What's the Dewey Decimal Classification number of that? Or what mammal is this based on the attributes of that mammal? So it requires those known labels. It requires that teaching up front, that supervised style, to actually come up with this classification that we're after. So our approach, given that we have a bunch of documents, given that we have existing tags, that we have the output that we want to get new tags and improve the ones that don't have tags at all, we're going to go for a supervised classification. We're going to use the joined-in tags that are already there, and then I'll do a demo where we're actually using the interactive tagging, where I'll classify stuff on stage and hit go, and we'll wait, and we'll see what the results are. I'm going to show you what's called, in very long words, multivariate naive Bayesian classification, which is less scary than it sounds, especially when you just take it as read that one of the calculations is good. What that means is you've got lots of variables coming in, and the naive part is the fact that we make some assumptions to reduce the problem. Someone said to me yesterday that classifiers in machine learning, they're all solving the same problem. Some of them just do it more efficiently than others, and it's all about reducing the problem space. We'll also have a very quick look, or an example of a Bernoulli multivariate I can't even say it this time in the morning. Bernoulli multivariate naive Bayesian classifier, kind of worked, which is a similar kind of approach, but it takes information about when something isn't there alongside when it is. So the steps in machine learning, I vaguely touched on this before, but they're really straightforward. You've got a couple of phases. You have the training side, which is feature extraction, and then your modeling. And then the prediction, which is taking the same features out, which I'll talk about in a sec, and applying that model. So once you've got the model built, which is the tough bit, the actual application of it, it's a pretty straightforward affair. So training, the supervised learning part, where we're actually plugging in those documents and plugging in those labels as we go through. We start off with feature extraction. Now, one of the things about machines, about computers, is there's no inherent understanding of any of the stuff we chuck at it. They're just ASCII characters, it's the bytes underneath, and so on. We've got to find a way of describing a document in an objective sense, rather than saying it's rather than just kind of saying, oh, this is about PHP, we need to actually say, well, it's got the word PHP in it, if you like. So we boil a document, an image, or any set of data down into numbers, and we do that in a consistent fashion, so that we have this multi-dimensional concept of what a document is. Take it to the numbers, and then the computer can work with those, add those together, multiply, whatever we want to do with them. But the important thing is that it's consistent, and that once we've applied that to one of our documents, we're going to take those same descriptors, those same features that we're extracting, and apply them across all our documents, so that we put them into the same kind of space, and we normalize them, if you like. There are many approaches. Basically, anything that you can apply to a set number of documents that turns into a number, you can make it a feature extractor. So term frequency, how often does this word appear, how often does that word appear, and so on in my line of text. We've got a fun one, term frequency by inverse document frequency, which is basically how important is a word to the document you're looking at versus all the documents. So this is kind of how search engine started off. I don't know if Google ever used it, but I'm pretty sure Alta Vista started off using it. Basically, you know that the word "the" is really common, so you need to, the fact that it appears in all your documents, while the fact that it appears really often in a document might make you think naively that it's important, the fact that it appears in all the documents a lot needs to be ruled out. So in that respect, we can actually bubble up important keywords as we come out. N-grams, which are basically 1, 2, 3 words in a row. So it might be that instead of saying if a specific word appears, we want to see if 2 words appear next to each other, or 3, so bigrams and trigrams. We can infer. We can construct something. So if we're classifying people and we know their date of birth and we know that the date is the 18th of February 2016, then we can calculate their age, and that can be a number that comes out. Basically, as I say, anything that creates a number. And what we're trying to do is look at the data that's come in and figure out where those numbers and those dimensions correlate with the tag that we've come up with. So I mentioned about thinking about things in multi-dimensional space, 3D, 4D, 5D, ND. The kind of cool thing about doing this is you have a lot of side effects. You can think about it in a really interesting sense anyway. A document might be over here in 3D space, another document might be over here, and the very fact that they're quite distant means they're not similar. So we can use what's called cosine similarity to take 2 documents that we've described with these feature vectors, these collections of features that we've extracted, and we can look at the 2 of them and say how similar they are because we've modeled them in n-dimensional space, done a bit of Pythagoras, and figured out that they're far apart, they're not similar, or they're very, very similar. They use very similar words. So we can start thinking about things in a spatial sense. And I bring that all up only because it's really cool, and it's a way that we can take the inputs to machine learning and figure out relevancy as we go through. The other thing is that we can use the scary matrix multiplication stuff that, again, I've forgotten since my GCSEs and A-levels, but I will remember one day. So I talk about feature extraction. The text on the right might be a bit small for some of you at the back, but effectively, we step through each part of our input document, and this example, this talk. We can take out some of the common words that's called stop words and removing thes and from and have and to and so on. We can take the words themselves and reduce some of the problem set even further by doing something called stemming. which is where you take, you do your conjugation. If anyone ever did Latin, you do your conjugation on the words, and you come up with a common root of each word. So apply and applying boil down to the same kind of token, if you like. And then we kind of count them as we go through. So we build up a list of features, event.title.php, for example. We've got one up there, and so on, and we build that up as we go through. So we come up with a simple feature vector. Have I lost the mic? No? So that's kind of an example of what we've done there. What we can actually do is, again, we can take two words. We can go with reading everything as a bigram example, and that becomes another measure that we're going through. I seem to have copied a slide there. That's wonderful. So what we do after that point is... Oh, we've done that. No, there we go. So with the supervised learning, we have what we call a training set. So we have that information where we've got all these documents that are already tagged. We have these known knowns and that model that we're going to build from. And we start to make the assumption, and this is where some of the naive element of that, that Bayesian classifier comes in. We start to make the assumption that the tags that are in our training set appear just as often in there as they would in the whole of our set. So if the word PHP appears in 3/4 of all the documents on joined in, then in 3/4 of the new ones, we'll find that word appearing 3/4 of the times again. So we take that assumption and we start counting them, as I've just shown there, and eventually we'll take the number of documents they've appeared in, and divide that through by the number of documents we have as a whole, and figure out the number of times that it appears across the whole document. So in that learning stage, we extract those features, we go through those steps for all of our things there, we take those tags that we know already, and we build that correlation. So we're counting this tag appears when this word appears and doesn't appear when this word appears, and so on. So again, many methods of probability, but if we're assuming that our training set is representative of all documents that can ever be put into joined in, then we can say that the probability that a tag predicts a feature, so the probability that the word PHP as a tag predicts that the word PHP appears in the document, that's the number of items with PHP in the document and PHP as a tag, divided by the number of items with PHP in the whole thing. It might be a little early in the morning. It's almost afternoon, but you know, it's pretty straightforward. A better example, because that's pretty obvious, might be the probability that the tag PHP indicates that Symfony is in that document is the number of items with PHP as a tag and Symfony in the document divided by the number of items with Symfony in the document. We can also write that as the probability that feature given the tag occurs is that. So I'm going to use some of that notation as we go through some of the equations that I'm going to say. Just trust me on this one. In code, again, it might be a bit small for you at the back, but effectively what we're doing is we're looping through the number of things that we've identified in there. We've for each of the tags that we found, we built up the number of features that occur against that tag. So that's in our feature list as we go through there. And we're just there doing this division with a bit of cheating. So yeah, we've got our list. We're looping through each one of those. We're filling it out so that we have zeros at the point at which a feature hasn't occurred, so that even though that word didn't occur in a document, it occurred somewhere in all our documents, so that we're filling it in with 0. we do what we call what's called Laplace smoothing, which is basically make sure that we never get a 0 by adding 1 to the item on the top. Then we do a bit of cheating to make up for the fact that we've just massively biased our numbers. And in reality, I could find probably a lot better ways of doing that mathematically, but again, it's beyond me. So just adding that kind of tweak there is what we're doing, is cheating. And effectively, what we're doing is we're setting ourselves up for the application of Bayes' theorem, which is the probability that a tag is predicted by a feature, so that the tag PHP is predicted by the occurrence of the word symphony in our document, is equal to the probability of the tag appearing across all our documents times that thing we worked out a second ago, the probability that a feature is predicted by a tag, divided by the probability of that feature existing in all our documents. You don't have to remember that. I've said it. I've won the points. That's good. Now, this is Bayes' theorem. I've missed out the multivariate bit. I wrote a really nice blog post that explains it, and that's what you get. So the probability that a tag is predicted by features 1, 2, and 3 is the probability of that tag appearing, times the probability that the feature is predicted by a tag, feature is predicted, and so on, divided by... Yeah. That was a genuine yawn. Yes, and you can find that. Basically, all the steps, as I was working it out, I wrote it down, and it might make absolutely no sense to anyone, but you can see I've at least done the working. What we can do is we can identify bits. This is the prior. So this is the number of documents tagged with that tag divided by all the documents we've got there. Remember, I was talking about we're going to apply the assumption that the tags appearing in our training set are equally distributed against our tags everywhere. The number at the bottom, which is the probability that all of these 3 features exist in the same document, that's going to be fixed. That's just a number. That's not going to change whatever tag that we're applying this to. So we can kind of cheat again there. And like I said, classifiers are about reducing complexity to try and make things a bit faster and a bit more applicable. So if we just replace that with a z, we can just mess about with the numbers as we chuck that in. We can assume it's 1, that they're always going to be there, or we can find a nice balance that brings stuff out. At the end of the day, it's just like removing a constant. And frequently that's combined with the prior because, again, that one's fixed every time that we're going through. Or in code, again, I said simple machine learning. I think the first slide was of code was about 10, 12 lines. This one's, again, about 8. It doesn't do anything very much special, but again, we're calculating our prior at this point, so the number of times the label occurs versus the number of documents in the whole training set. We then are going through, do we have that feature in the model as we're doing this prediction stage? And if the answer is yes, then what we do is we actually just grab that probability that we've calculated previously. How often does the feature occur for the tag? And then we just multiply it together. So again, probability that tag is predicted by feature. And like I said, we then multiply. The problem with multiplication and all these things is we're calculating for big numbers of documents, we're calculating really small numbers, which is great for a probability when you're doing it once, but as soon as you start multiplying, it gets worse and worse and worse and smaller and smaller and smaller and dashy 27 and 80 and blah. So if we actually switch to using log, we can turn that into addition, not lose out on any of the numbers. It's just a different bit of transformation that we can do there. And we'll see a bit later that the numbers are very different. They also end up very negative. Again, beyond me. Oh, dear. So I'd love to build this up and say it's spectacular. It's wonderful. It's the best thing you'll see all day. It might be the best thing you've seen since the keynote. I'll go with that. Because it certainly doesn't beat that. So, here's a little web app that basically takes everything I've shown you, models it all in the background for all those 1,048 events and all those huge numbers of tags, 350, something like that, builds a model, then applies the classifier, and then just gives you the probability that a given tag is right for the event. So what we've done is taken the title of the event and the body. We've broken it down. This is a bit of a better one, DOM code. We've broken it down into the features that we have there. And I've namespaced them just so that I could use more than n-grams, as I was saying in the past. We then do all that multiplication together. We apply all those probabilities we've worked out in our model, and we work out that this is PHP is a really small number. The important thing is because that we're multiplying for each word in the document effectively, or each unique word in the document, that number is going to be relative to the whole thing. So we're looking for big differences. So we can see there's a huge level of difference between DOM code being about PHP, which it mentions PHP, we have a result, versus it being about the web is quite high, but you can see how we're actually picking up some of the ideas. We've seen some correlation about Symfony and Drupal as we go through. I was going to go through and figure out what a really good page to show you on was. Madison PHP is 13% likely to be about PHP, which is a result. It's a consistent result. Look. So effectively, that's what we're doing. We're taking those tags that we already have existing. We're doing all the multiplication together. I mentioned it was about 350 tags. This is only done over 20 because, as I'll show you a little bit later, there are some slight memory issues in doing this kind of thing. And again, that's I've reduced the problem by chopping out 330 of the tags for this model. I mentioned about using logarithms. So instead we can have actual numbers, just shifts the problem into something that we can deal with a bit better. And so on as we go through. Now, this model, when I built it, took about 23 seconds. I'm now going to switch it to using n-gram bigrams. I'm now going to hit build the model, and then we're going to wait. It's going to fail. I'm going to have waffled for 23 seconds for no good reason. I'm going to cry and then switch to another demo just to show you some of the interactive kind of ideas as we go through. I think we've still got about 15 seconds left on this, so I'll keep going. One of the things I found through doing this is I'm not necessarily the best at it yet. I'm getting better. Yay! Memory issue. Let's go back to where we were. We can't. Lovely. Like I said, it failed. And this is an important lesson. Don't go off-piste when you're doing a talk. Skip to the next demo. One of the things I didn't talk about there actually was the fact that we've got the multivariate Bayes, which is doing all that multiplication together. But that's basically saying if a word exists there, what we do is actually multiply when we encounter it. Bernoulli, that I mentioned earlier, actually models for all the words that you've got, and if it works out the correlation not only of when the tag exists and a word exists, but when a tag doesn't exist and the word exists, and tries to figure out where you have the probability that something doesn't predict and the probability that something does predict as we go through and merge that together. It's a fairly straightforward process. Again, I'm going to give you a link to the code later so you can pick through that as we go through. This one is more interactive, and this shows kind of the interactive supervised learning side of things. So this is halfway house to that machine, that human tagging I was talking about being boring as we go through. This is how I know it's not quite a minute to do each one, because that's about PHP, that's about PHP, that's about PHP. Are you getting a theme? That one isn't. Excellent. And so on as we go through. We can then submit that through. We can build our model as we go through. This one's just working down on the actual titles as we go through, just to speed up for the demo and so on. We can see that using the Bernoulli side of things, we're saying it's either PHP or not PHP. And we can see that because we have an interesting mix of languages in here and place names, we can see that Friday apparently is 100% correlated with PHP. Whereas JS days, yay, is positively correlated with not PHP. There are a lot more tags as we go through here, but this just kind of gives a flavor of what we're building up in the background. I've constructed a confidence score, which is relatively random, because we're taking 80% of our knowns. We're building our model from that, and as a result of that, we're checking that against our 20% left over of knowns to actually figure out how well we're doing. If I had a bit more time in preparing this, I might have actually created a feedback loop that you could use that confidence score, how many times did I get it right against what I know versus how many times I didn't, as a kind of a fitness function to help say that this is a good model and this is a bad model and so on, and start tweaking the inputs, some of those numbers, the cheating numbers, some of the weights, if you like, so that we can start building up a more complex picture. But for the purposes of this, we can see where our successes and failures are, including in CSS, and where we're getting stuff right and totally wrong as we go through. So, so that was the scary and didn't quite work demo as we go through. All of that code is gone now on the floor. All of that code is going to be up. I'll give a link to it later, especially after I've finished the hacking. That'll make it look good. So you can follow that through. So given that I've now demonstrated a bit of failure, having been so positive going on the way through, we had a bit of human learning to do as I went through this process. I talked about how I learned, or how we learn as humans, but this experience is fed into that, the cause and effect side of things. So, lessons I've learned. Bayes' theorem is annoying. Just trust that it works. Because at the end of the day, it's all about multiplication, division. It's just those kind of figure out the numbers, plug it all in, let it fly, do its stuff. Joined in, it turns out that Larry Garfield was very correct in considering it to be a fairly accurate proxy for PHP conferences, because it's very heavily PHP biased. I've built something that pretty much labels everything as PHP. It's not that's uncharitable. It's because at the end of the day, most of the data coming in is about PHP. We've made that assumption that it's representative of what's actually out there in the wild. And so if we've got a lot of prevalence of PHP in our training set, that's going to be reflected in our output as we go through. A lot of the tags are noisy. I could have stepped through and shown you that the members of SoFlow PHP really love to tag themselves with the SoFlow PHP tag. As do PHP Hampshire with PHP Hants. And as a result, because it appears quite a lot in our training set, we start thinking that things in Paris are in southern Florida. Again, that's not something that we can correct overnight with the data coming in, but it gives us an opportunity to actually figure out what features might better to describe stuff and kind of quelch that noise as we go through. All this approach, we're building up lots of grids, lots of numbers, lots of multi-dimensional arrays. That takes a lot of memory. 350 tags, which is what I was trying to calculate this with when I started, by about 13,000 features. 76 bytes to put one item in a PHP array. That's lots of memory. That's 300 and something megabytes worth of memory. And that's only going to get worse as you add more names. So one of the things that we're learning by the hard way is that we need to actually be a bit more discerning. Are we building classifiers for one tag? Are we only going to pick out the actual signal features, so the ones that appear lots versus some of the ones that don't appear much at all, or the ones that that have high or very low correlation and ignore the ones that are middling and so on to reduce that problem. Like I said, classification is actually, the difference between classifiers ends up being how you can reduce that problem set so you can fit it in memory or you can fit it into the constraints that you already have. So my next steps, as I said, I need to improve on my feature selection. I need to actually start picking out bits from that data set that are actually indicative of signal and stuff that I can combine in a better way and improve that confidence score that I've shown you there. To implement different types of classifiers, so I can't just stand up here and say to you, Bernoulli multivariate naive Bayesian classifiers, and go on a bit more and talk a bit better on that. You can build the model into joined in. That model, even though I've now lost the numbers, was applying itself very quickly. It was applying itself in about 30 milliseconds once we've actually loaded it up. Pass in a new document, it would take 30 milliseconds, and you've got a tag or a set of tags out the back of it. So all the pain is in that creating of the model, maybe in some of the loading of the model, but when it's applied, it's really quick. So if we found some way of applying that as you submit your documents, that would be a lot quite useful, hopefully, in the future classification of joined-in talks. And again, improve the performance, actually figure out how matrices work, actually add caching and do stuff that's a bit more rigorous than I have been as part of this. One of the things that did come out, having applied all these classifiers and given it a shot, is this is the original output. Well, I say the original, it was calculated this morning. It's the original form and the original method that Larry Garfield came up. This is where I was picking out the fact that we have JS Day popping up with 24 talks and 57% new speakers. You've got, I'm not entirely sure what that conference is there, but it's 98 talks and 100% new speakers. That's quite a lot of noise, and that's the problem I was starting to look at. And you can see down the bottom here, the overall number currently, as of this morning, is about 49% of new speakers in our proxy PHP side of things. If we actually look at something I've classified, which has taken out some of those some of that noise. It's left in a few of them, but it's taken out some of it, and we actually see that our results start to shrink down to 44%. And when I actually get the classifiers right, I'll publish the numbers there and feed that back. And we can actually look at how we've gone through and improved that diversity of our new time speakers, our first-time speakers. So, you can find, I promise, the code. I'm creating a library called Enamel, which has currently multivariate and Bernoulli multivariate stuff in there, and some of the ways in which you can actually feed your own documents in and your own tags and so on. The joined-in audit stuff, created, as I said, by Larry Garfield. I've made some alterations to provide that webhead and to bring in Enamel and so on into it. But effectively, you can go to those places and check my working and check that the figures actually match what I've actually shown you not doing today. So, with that, thank you very much. And have I got any questions? Billy?
So I guess you can define a lot of these similar things in Elasticsearch and generate the same sort of statistics using aggregates. I was wondering how your code compares to something like Elasticsearch, which has been around for a little while. How does it perform in comparison? Do you get the same sort of results?
I assume you'd get the same sort of results. You just would have something that's a hell of a lot less performant. So this is more an exercise in not in making a fast thing, but actually implementing it myself. and putting it forward. Yes, there are a hell of a lot better stuff out there. There's scikit-learn in Python, which is the industry standard for the coding side of things. You can get better storage. This is backed with MySQL. You can get all that kind of thing there in a way that PHP, in the way that I've written it anyway, is a hell of a lot less performant about. But this is an example of showing that hopefully anyone can do it because it's so simple.
Just had a quick question about the interpretation of that 13% that came up earlier, that given something is tagged as PHP, there's a 13% chance that it actually is about PHP.
So it's more that was the cumulative probability. And because we're multiplying in that example without correcting for it, we're multiplying the fact that it's not just got PHP in there, but it's got all these other words together that are existing in other documents. That reduces that number down even further. So the way the numbers were presented is more about the comparison between the different tags themselves for that document rather than as a whole. So it's reduced by the fact that, I don't know, you had a common word that showed up in JavaScript, say talks, in different documents. So it's not necessarily, there's only a 13% correlation in...
How should that be interpreted?
How should that be interpreted? It's the fact that it's most likely of all your tags to be applied. So PHP was at the top. It was the highest number, even though it was a relatively low number. It's the highest correlation for that given document. A better approach might be to say normalize for that. We've got very different sizes of document there. So a better approach might be to say have some kind of, if you're heavily weighted there versus all the other tags, it's most likely to be about that. And as a result, the actual number itself doesn't matter, but the comparison with all the other numbers that you've generated for that model would be a better way of doing that.
Hi. I mean, I saw the time it takes to actually execute the result. Do you have any thoughts about the memory management on this case? Like, for example, just using PC may not be enough for the hardware.
The approach that I've done here, you could probably do it in a more scalable side of things. You could do all sorts of things to actually spread the load out. The better approach in my example would actually just to be reduce the amount of information being calculated all the way through. So I'm not actually trying to use the memory in the first place. So as opposed to using it more efficiently, I use it more efficiently by not using as much of it, if that kind of makes sense. So instead of saying calculating all that data for 350 tags, try one tag at a time. Or reduce the number of features I'm calculating so that I've got less information that I'm trying to calculate for each of those tags.
Thank you.
Do you think it's ever useful, or when might it be useful? Sorry. I wonder when it might be useful, if it's useful to manually edit the model after it's generated. For example, you said that Friday was 100% correlated with PHP. Is that the sort of thing you might want to manually delete after you've generated the model or not?
So there's no reason why you couldn't do that. So kind of prune what's going in. The advantage is we know that's a ridiculous thing. But one of the interesting things of machine learning is the fact that it might be that PHP only ever gets talked about on Fridays. And you might assume that we talk about it every day, but in actual fact, on Joined In, it only ever gets talked about on Fridays. And machine learning, doing this and showing the actual numbers and calculating that, might actually show you a correlation and a result that's entirely counterintuitive, but might be entirely accurate. So yes, you could manipulate the model that you've created, and that would be valid, certainly in that example, but that's making the assumption that we know right, and not the thing that's actually crunched the numbers. So I think there's only a couple of minutes left to actually go and get your coffee. So why don't you take a break now? Thank you very much for your questions. If you'd like to get in touch,